Hello, everyone, I am Jingdong from Zhejiang University. In this video, we would like to introduce our work, Location-Aware Single-Image Reflection Removal. Reflection often occurs when taking photos through transparent media such as glass, which will downgrade the image quality. Photographers usually use physical devices such as polarizers to remove reflections, but they cannot avoid color distortion. Single-image reflection removal is a highly ill-posed problem since we need to decompose and obtain two layers at the same time. For this, previous methods introduced many priors such as gradient sparsity, relative smoothness, ghosting cues, to constrain the solution space. Recently, some deep learning-based methods have been proposed to solve this problem by learning the task-specific features such as edge hint through neural networks. In our work, we observe that the reflection location information is rarely investigated in deep learning-based SIRR methods, and this information is a useful cue to handle strong reflections. In addition, strong reflections such as the highlights cannot be effectively removed by previous methods. Therefore, we propose to learn RC maps for detecting reflection-dominated regions and removing reflections instead of recovering the transmission layer via gradient details. Our RC map participates in the prediction of reflection and transmission layers, which controls the subsequent feature flow, resulting in significantly improved SIRR results. Besides, there is no ground truth RC map used for supervision. This can avoid the difficulty of defining or labeling reflection-dominated regions. Furthermore, we observe that low-frequency reflections are less evident in the Laplacian map than in the edge map, which suggests that the Laplacian operator, as a second-order differential operator, can suppress the low-frequency reflections more effectively. In contrast, strong reflections that have hard boundaries cannot be suppressed by the Laplacian operator. That's to say, the difference between I and T, caused by strong reflections, becomes more obvious in the Laplacian domain. We assume such a behavior of the Laplacian operator is beneficial to detect reflection-dominated regions, and we propose to design a recurrent network, obtain multi-scale Laplacian features of I and the predicted T, for detecting strong reflections. We extract this feature by convolution operation, and initialize the convolution kernel as a Laplacian kernel, update it when training. To maintain the properties of the Laplacian kernel, we also apply gradient clipping to the learned kernel. Our proposed model is a two-stage recurrent network, and it restores transmission layers in a removal by detection manner. We design stage 1 to detect the reflection-dominant regions, and predict the reflection layer by suppressing the transmission information. Then, stage 2 restores the transmission image by leveraging the transmission-dominant regions and the predicted reflection layer. We design RDM to obtain multi-scale Laplacian features via 4 groups of Laplacian convolution kernels, and predict RC map by 3 SCRS blocks. We also design TSM to refine the Laplacian features, suppress the transmission features via RC map. Then, the contextual autoencoder in stage 2 is used to predict transmission images by jointly leveraging the inverse RC map and the reflection layer. In particular, stage 2 can remove weak reflections without accurate RC maps as inputs. For training loss, we propose a novel composition loss to supervise the RC map T and R, based on the blending model in a weak supervision manner. Other losses such as pixel loss, SSIM loss, perceptual loss, adversarial loss, are adopted to improve the image quality. We compare our model with 7 state-of-the-art methods on 5 real-world datasets. From the table, we can see that our method achieves the best average PSNR and SSIM scores. We also show the iterative refinement results of the transmission images, reflection layers, and RC maps. The reflection-dominated regions are gradually evident and accurate in our RC maps, and the reflections are removed more thoroughly with the iteration number increasing. Besides, it can be seen that existing methods typically fail to remove large area reflections and strong highlights. In contrast, our method can remove the most undesirable reflections while preserving high-frequency details in the transmission layer. Thank you for watching.